All right, so this talk is about first order rewritability for OMQs in roughly Horn logics. Okay, and it's joint work with Weddell as usual. So this topic has been looked at by others as well. So let me just quickly talk what's new in here. So one thing which is new is we talk about one of the logics we developed for reasoning about database schemas and associated approach for answering queries or generating certain answers. But the more interesting part of this paper is that it links first order rewritability to best definability via Clark's completion and via the combined approach. So roughly the results in this paper are, as I already said, linking rewritability to definability, being able to actually derive rewritings using correct interpolation for if they exist. And then there are some free goodies such as integration of database integrity constraints, the constraints for which the A box generated by database is not only consistent with the constraints, but is actually pretty much a model. And of course, query specific OMQs will be just a freebie here. Okay, so quick background, I try to make this as short as possible. In our logic, we can have complex subsumptions, but they all boil down, at least in the simpler versions of the logics, to the 6 cases you see on the top of the slide. And the unusual thing here is the last production, which is roughly an extension of functional dependencies to much more complex path functional dependency, which roughly says if A and B agrees on what's in front, on the path in front of the arrow, then they agree on the path behind the arrow. We see examples in a second. And as I was saying, the additional constraints we have to put on the syntax to make reasoning in P time. The way it's presenting here is reasoning X time, but it will not matter for the results today. It's X time complete actually. And the semantics is the usual. Concepts are subsets of the domain, features are total functions or partial functions if you wish, and there is knowledge bases and A boxes and T boxes, all the standard boilerplate. Okay, so before I go to the details, why do we deal with this logic? Why do we like it? That's because if you deal with databases, you can see these 2 create table commands, and you will think about, well, what does it really mean? And it really means what's written in the left column of this next slide, almost exactly. Okay, that captures almost everything in the 2 create table commands. But then, because we can write this as ontology, we have other capabilities. We can specify inheritance, we can have local typing, we can, using our extended functional dependency, we can say things like employees and departments cannot have the same name because they're disjoint concepts, and so on and so forth. Okay, so this was a database commercial. Back to the topic. So we still need to say some conjunctive queries. The usual thing, atoms in the conjunctive queries corresponds to A box assertions, roughly speaking, with variables instead of constants. And queries are existentially quantified conjunctions of this kind of atoms, or unions or disjunctions of such conjunctions. And certain answers are tuples of constants, which when plugged to the free variables of the query, make the query entailed by the knowledge base. So that kind of tells you one approach to dealing with generating certain answers in decidable logics is trying to run the entire problem. Decidable logics means they have to be decidable including this conjunctive query in here, which is typically not part or not representable in the knowledge base itself. Now, if you want something more practical, there were many proposals designed and presented for computing certain answers, which started with the so-called perfect rewriting, which takes the query and rewrites it with respect to the knowledge base, and the new query then can be run on the A box as if it was a database. Now, we cannot use that in our logics because the data complexity is too high. It's complete for P time, and therefore we know there cannot be first order rewriting for every possible situation, for every possible OMQ. So some time ago with Karsten, we had this idea for the EL logic, which is the same problem. And we essentially said, well, instead of completing, rewriting the query, we just massage, so-called complete the ABox data. And we complete it enough such that we can run query on top of it, which will give us the certain answers. And this works for EL because EL can only generate, roughly speaking, finitely and few distinct anonymous types. So that still doesn't work for our logic because we can actually enforce exponentially many anonymous types in any model. All right, so how do we deal with it? So that came to the combined approach, which may not be the best name. It kind of combines perfect rewritings. We rewrite a query for the anonymous objects with Datalog style completion of the data, which deals with our p-time problem. And if you do it correctly, you get a result like this, saying certain answers are the answers to the modified rewritten query over the result of a Datalog program or the minimal model of a Datalog program, if you wish. And extension predicates for this Datalog program come from the ABox, of course. Okay. So now if you look on this blue formulation, the highlighted formulation, it kind of tells you, well, fine. It really boils down to the question, can the Datalog program somehow be replaced by first order queries or not? We want to decide that, really. So how do we do that? So here is example of how the Datalog clauses are generated from our TBox, and you have to do it for all the consequences of the TBox, but because you have to only do it for these 4 special cases of subsumptions, you can essentially enumerate those in cubic size, roughly speaking. Okay, and then you look on it and say, well, yes, we can run a Datalog program, but we have no idea whether that's first order definable. And let's start with a simple case. We want all these CBs, which are the Datalog predicates standing for the primitive concepts B and A and A1 and A2. Are they definable? And then we worry about general queries later. And if you think about it for a second, you find out, no, not a chance right now. There is no data where there are these feature atoms in here, but there is no data from the no reasonable data from ABox. But you quickly find out that even if you add the ABox under the open world assumption, so that's these clauses in here, we just say what's explicitly represented in the ABox, PB, which is essentially closed predicate, implies the derived facts about B's. Okay, and the arrow can go just one way, because if it goes both ways, it's a closed world assumption, and that creates problems at many places, including complexity stuff. Okay, so we cannot do that directly. On the other hand, to use definability, we need some kind of closed world assumption. So this is the crux of the paper, really. We flip through our old papers and find the paper by Keyes-Clark, and which defines so-called Clark's completion of a Datalog program. And so the Clark's completion, 1977, was defined to reason about semantics for Datalog programs with negation as failure. And we use much simpler formulation of the Clark's completion for this paper because we have no negations in here, roughly speaking. Okay, so how do we use it? So if you look on the definition, if you look on the definition in here, what does it really, what the completion really is? It's kind of collection of all the clauses which define a particular CB predicate. You put them in disjunction, and then you say that CB predicate is actually defined by this disjunction. Okay, so that's very simple. But there's this nice property. If you put it together with your ABox clauses and any set of EDB facts, ABox assertions, if the Datalog program entails a fact, then the closure Clark's completion entails the same fact. if the Datalog program does not entail a particular fact, which means that fact is not present in the minimal or canonical model, then the Clark's completion entails its negation. And if you think about it, that's essentially the closure we've been looking for. Because now we take another old paper by William Beth from 1953 and say, oh, when we can define the CBs in the Clark's completion, we can find a formula which is equivalent to CB in a restricted language. In the language of what? In the language of the A-box. So this piece are the predicates which are explicitly defined by the A-box, and the R's are all the role assertions as well. And it kind of says, first order rewritability for atoms or primitive concepts over T boils down to definability over the Clark's completion of T, over the A-box atoms, the signature of the A-box. All right, we can do slightly more than that. So we can construct the rewritings by just observing that it's something on the lines of this logical implication. And if you look carefully, or you find out that the whole thing can be formulated in ALCI. So that gives you upper bounds in X time, which are compatible with the other bounds. And using correct interpolation, we can actually generate these things from the proofs. Okay, last thing, second last thing, database constraints. You just add more formulas to your Datalog program. And essentially what you are saying the things which are derived must now be explicitly present. Okay? And that will improve your chances of finding a rewritable thing. And I just want to concentrate on this last little bit, which says, well, all right, manager becomes definable with non-trivial interpolant, non-trivial definition. It must be an explicit employee who is manager of somebody. And you can generate this completely for free. Same for queries. So we have one way, if all the atoms are definable, then queries are definable. But we can plug in the queries in the interpolation problem to find out the queries which are definable, even though not all its atoms are definable. There's some fine-grained complex analysis, which I won't talk about here. There's lots of problems to think about.
Okay.
Lots of problems to think about. You can look about it in the paper. I want just to go to this last little bit. So we want to thank to the reviewers for the last two suggestions. Does this work for non-Horn logics? And now this is a little tricky because you have to extend the combined approach and the Clark's completions to non-Horn setting. That's not entirely trivial. And does it work for separation for higher complexity classes? And that's very unlikely because this depends on compactness and definability. And with that, I open for questions.